Hey guys, welcome back to another Algebra 2B video. This time we are talking about lesson 11.4, compound events. If you recall in 11.3 we talked about events that are independent or dependent, where one event depends upon what happens with the first event that took place. This is a little bit different. So the probability in the math is a little bit different, but the concepts aren't all that dissimilar, and you'll see what I mean. So a simple event is an event that describes a single outcome. Drawing a card from a deck, rolling a die, flipping a coin, those kinds of things. A compound event is an event that is made up of two or more simple events. And there's two types of compound events. The first is what we call mutually exclusive events. These are events that cannot both occur in the same trial of an experiment. So if I roll a die, for example, rolling a 1 and rolling a 2 can't happen on that number cube at the same time. So those events are what we call mutually exclusive. I think I have this Venn diagram here where you've got event A, event B, and there's no overlap whatsoever. The math for mutually exclusive events is this: the probability of A and B, or I should say A or B, because this is a union, so it's or. A or B is really the probability of A plus the probability of B. Recall in the last lesson we talked about how you multiply when the events are independent, or even if they're dependent. Now we're going to be adding. So it's the probability of A plus the probability of B. So, for example, when a number cube is rolled, what is the probability that you get less than 3? Well, that's the probability of 1 or 2. Two events there, so 1/6 plus 1/6. The probability of getting a number less than 3 is 1/3. And here's an example to show you what we mean. A drink company applies one label to each bottle cap. You either get a free drink, a free meal, or you have to try again. So the bottle cap has a 1 in 10 probability of being labeled free drink, 1 in 25 of being labeled free meal. Why are the events mutually exclusive? Well, because there's only one label per drink. So you can only have one or the other. It cannot be both. So what would be the probability that you get one of those things? Either you win a drink or you win a meal. You would be adding them up. 1/10 plus 1/25. Remember, in order to add fractions, we need a common denominator, in this case 50. So it's 5/50ths plus 2/50ths. You get 7/50ths. If we go over to the note packet, let's talk about this. So again, this is kind of what we just said. We've got a simple event is an event that cannot be broken down any further, and compound events are made up of two or more simple events. Mutually exclusive events, like we've talked about, are events that cannot happen at the same time. Now, their example is drawing cards from a deck. What's the probability of drawing a 5 or a face card? So we either going to draw a 5 or a face card. And or there's the big key, right? One or the other. Well, they can't both happen because there are no 5s that are also face cards. So the probability of drawing 5 is right here. 4 out of 52 or 1 out of 13. The probability of drawing a face card, if you recall from the lesson yesterday, it's 12 out of 52 or 3 out of 13. So the probability of one or the other is going to be the sum of the two. It's going to be 4 out of 13. So let's take a look at some of these here. And all right, so we're drawing cards from a deck. Tony, what is the probability she gets a number card or a king? All right, so the number cards, remember there's 40 out of 52, those guys. And I think I'm just going to leave it there. I guess I could simplify that. Let's see, what would that be? Yeah, 40 out of 52 is 10 13ths. Probably drawing a king. How many kings are there? There are 4 kings. 4 out of 52. That is a very small number. 1 out of 13. All right. So, number card or king. Add them up. 10/13 plus 1/13, 11/13. All right. Probability of an ace or a queen. Okay, again, these are mutually exclusive because they can't be both. So the probability of an ace, again, 4 out of 52, which is 1/13. Queen, again, 4 out of 52, which is also 1/13. So the probability of an ace or a queen is going to be 1/13 plus 1/13, which is 2/13. Now it's nice when your denominators are the same, but just remember, again, if they're not, you may have to combine like terms and get a common denominator and all that fun stuff. All right, so let's go back to the textbook here, because now we're going to talk about inclusive events. Inclusive events are events that occur that have one or more outcome in common. When you roll a number cube, if I say what's the probability of rolling an even or rolling a prime, those are not mutually exclusive because 2 is a prime number. It's both. So here's the Venn diagram for that situation in particular, but you're going to have some overlap here. The even numbers are 2, 4, and 6. The prime numbers are 2, 3, and 5. So 2, excuse me, counts for both. So you don't want to count it twice. If we just add up these probabilities, it's not going to be accurate. So what you're going to have to do is you're going to have to actually subtract the possibility of both things happening at the same time. If you want to know what the probability of rolling an even number and a prime number, so again, inclusive events are going to be and situations, you're going to have to add up the probability of one plus the other and then subtract the probability of them both taking place. And it basically looks like this. So the probability of two inclusive events, A or B, occurring is the sum of the individual probabilities minus the probability of both. So probability of A and B would be the probability of A plus B minus the probability of A or B. So them happening both at the same time. So here we would have even or prime. Well, even, there's 3 out of 6. Prime, 3 out of 6. Well, we know it's not going to be 6 out of 6 because there are numbers on there like 1, for example. That's 1 is prime, isn't it? No, 1 is neither. Okay, so you got to subtract that even prime 2, and you get 5 out of 6. Might help looking at these. These are some weird looking. Oh god, now they got number spheres. Okay, so find the probability on a die rolling a 5 or an odd. All right, so the probability of rolling 5 is 1 out of 6. The probability of rolling an odd is 3 out of 6. But 5 is also odd, so what's the probability that it's 5 and odd? Well, it's 1 out of 6, so we're going to subtract that, and we just end up with 1/2. The probability of rolling at least 1 4 when rolling 2 die. Okay, so probability of rolling 4 or 4. Well, the probability of rolling 4 is 1 out of 6. On the other die, it's going to be 1 out of 6. But they said at least 1, so we're not going to count the situation where they might both be 4, which would be 1 out of 36. So we have to subtract, and so you end up with 1/6 plus 1/6 minus 1/36. You get 11 out of 36. A little bit more difficult to conceptualize this stuff. Maybe it will help to look at cards. Cards tend to help because you've got suits and you've got numbers and you've got face cards, and you can have one or the other or both. So let's take a look at this. Decide whether these events are inclusive. A card is drawn from a deck. What is the probability of drawing a 3 or a heart? Okay, so these are inclusive. Why are they inclusive? Because there is a card that is a 3 and a heart, so they overlap. So we're going to find the probability of drawing a 3. That would be this guy here, 4 out of 52 again. The probability of a heart is 13 out of 52. But then we have to figure out what is the probability of a 3 and a heart. Well, there's only one 3 of hearts, so it's 1 out of 52. Now notice they did not simplify these. because they're already all the same denominators. And if we're adding and subtracting, we kind of want their denominator to be the same. So don't simplify if you don't have to. So here we're going to have that 4 out of 52 plus 13 out of 52, and we're going to subtract the 1 out of 52. So you end up with 16 out of 52. Now we can reduce. It's 4 out of 13. Cards make it a little bit easier, I think, than talking about odds and die rolling and stuff like that. So let's see. All right, Charles. Charles is drawing from a deck. He draws a red card or a king. What's the probability of a red or a king? So the probability of red is actually going to be, well, gotta switch. Probability of drawing a red is 26 out of 52. Half the deck is red, right? Probability of a king, there are 4 kings, 4 out of 52. How many red kings are there? That's 2 out of 52. All right, so we've got all our probabilities here. So what we're going to do is we were going to add them together and subtract. So we're going to get 26 out of 52 plus 4 out of 52 minus 2 out of 52, which is really just 28 out of 52, which will reduce. But notice I'm waiting until the end. It is 7 out of 13. A diamond or a face card. All right, so diamonds. There are 13 diamonds. Face card. There are 12 face cards. So we got 13 out of 52, 12 out of 52. There are 3 face cards that are diamonds. King, queen, and jack. So, add them up and subtract. We got 13 out of 52 plus 12 out of 52 minus 3 out of 52 is 22 out of 52. How do you do that so fast? I'm smart. There's also a calculator next to me, but you'll know when I use it. 22 divided by 52 is, all right, weird, 11 out of 26. Oh, okay. So that's basically it. If we go back here, there are other examples other than gambling and playing cards. If we look at example number 3 here, there were 3,510 drivers surveyed, 1,950 were male, 103 were colorblind. Only 6 of the colorblind drivers were female. What is the probability that a driver was male or was colorblind? All right, so there is some overlap here because only 6 females were colorblind. And so it helps, I think, to create a little Venn diagram here. So we got all the male drivers, 1950. We got all the colorblind drivers, only 6 of them were female. So there was 103, that means 97 of them were male. That means that leaves 1,853 males that were not colorblind. And I go through the steps here. So what's the probability that someone picked at random is male or colorblind? So you get the probability they're male plus the probability of colorblind minus the probability of both. And you end up with 1956 divided by 3510, or about 55.7%. So really, those Venn diagrams, I think, will help you. If you remember in lesson 11.2, complements of events with probability of p, you just subtract from 1. Often it's probably easier to find the complement of an event and just subtract it from 1 in order to find out the probability of what you're asked to find. If we look at this example here, there are 5 students in the book club. Each student randomly chooses a book from a list of 10. What is the probability that at least 2 students in the group choose the same book? So we could have 2, 3, 4, 5, 6, 7, 8, or all 10 of them choosing the same book. That would be really hard to figure out. So why don't we just find the probability that they all pick different books and then subtract that from 1. Because if everyone chooses a different book, then that's really the opposite of at least 2 choosing the same. So how do we figure that out? The probability that they all chose a different book is going to be the number of ways 5 students can choose different books divided by the total number of ways they can choose books. So it's a permutation because order does matter because we want them to choose books that are different. So it's going to be 10 pick 5 for different books. And then the total number of ways they can pick, well, we got 5 students. They're each picking from 10 books, so there's 10 choices for each, 10 to the 5th. So the probability that they all choose different ends up being this, 30,240 divided by 100,000, or about 30.24%. So now the probability that at least 2 students chose the same book would be 1 minus 0.3024, or 0.6976. So about 69, I would say 69.8, or in this case 69.76%. So sometimes it's easier to find the complement and then subtract from 1 to figure out what you're trying to find. That's going to happen when you've got multiple situations going on, and you'll know based on the homework. What I want to do is I want to go back, because I did include this excuse me, in the note packet, just using a Venn diagram. And because I've already said a couple times that this is very helpful. So here are the 2 types we're talking about. Remember, these mutually exclusive events, there's no overlap at all. We don't really need to worry about a Venn diagram for those. Just going to add them up. It's really going to come into play with the inclusive events, where you've got some overlap. So if we look at this, again, we're talking about cards. That's easy. What's the probability of drawing a red or a face card? Well, I think we did something very similar to this already. So let's see, there's 26 red cards and there's 12 face cards, but there are 6 red face cards. That means there's 20 red cards that aren't face cards, and there's 6 face cards that aren't red. So these are inclusive events because there are some that can be both. There are 6 red face cards, 3 hearts, 3 diamonds. So this is where that Venn diagram comes in handy. So you would have, remember, what would we say, 20, I'm going to change the color just for fun. So you would have like 26 out of 52 plus 12 out of 52. But you would have to subtract 6 out of 52. So we're looking at this, we're looking at this, we're looking at that. So let's see, let's try to draw a Venn diagram for these situations. Of the 2,250 voters surveyed, 1,580 voted in the last election and 630 are planning to vote for Miller. Only 150 of those who voted in the last election are planning to vote for Miller. All right, so we've got 2 things here. We've got mutually exclusive stuff going on here. We got a total of 2,250. We've got, I don't like my circles. I'm going to redo them. Hold on. Ooh, I'm going to try shapes. Oh, look at that. Oh, no. Where'd you go, shape? I got to do it again. No. Forget it. I'll just draw my circles. Just want them to be nice and big. Alright, so that's even worse. We've got a total of 1,580 who voted in the last election. We've got a total of 630 that are planning to vote for Miller. We've got only 150 of those who voted in the last election planning to vote for Miller. So 150 are right there. Miller must suck. Okay, so what's left? Well, we got 1580 minus 150. We got 1430 over here, and 630 minus 150. We got 480 over here. So if you're trying to figure out, who voted in the last election or who plans to vote for Miller, you've got to do that. Restaurant served 253 customers last night. The staff reported that 189 customers made a reservation and 163 customers used a credit card. And only 47 who used credit card did not have a reservation. All right, so we've got this, and we got this, and let's see here. All right, so again, 253 customers last night, 189 made a reservation, 189 made a reservation, 163 used a credit card. 47 of those who used a credit card did not have a reservation, so we got 47 over here. So that means of the 163, we subtract 47, we have 116 who made a reservation and used a credit card, and then that means we've got 73 who made a reservation but did not use a credit card. So again, if you read it, you got to see what's going on here. So that's that. Anyway, your homework is in Schoology. Go for it. If you learned something today, smash that like button, and I will see you in the next one.